Now let us take a look at the so-called atomic mass units. What is the atomic mass unit? Well, it's denoted with the letter U, and 1 U is equivalent to about 1.6605 times 10 to the negative 27 kilograms. Obviously, it's a very, very small mass. Now, why this number? Well, it turns out this number is roughly the mass of a proton or a neutron. You know, the thing is, you look at an atom, it's made of course, the atomic nucleus and the electrons, right? It turns out the electrons have very, very little mass compared with the nucleus. So basically, the mass of an atom is roughly equal to that of its nucleus. And a nucleus is made of a whole bunch of protons and neutrons, each of which roughly with the same amount of mass, roughly speaking. Okay, so basically, the mass of a particular atom really depends on how many neutrons or protons it has. And if each neutron and proton roughly has this much mass, then by counting the number of neutrons or protons, we can figure out roughly how much mass each atom has. The number of neutrons plus protons, therefore, determine roughly the mass of the atom, and we call that number the atomic mass number. For example, aluminum has 27 neutrons and protons. Therefore, the atomic mass number of aluminum is 27. So we say, roughly speaking, the mass of an atomic atom, of an aluminum atom, is about 27 U. Or we say, again, the atomic mass number of aluminum is 27. Okay, what's so good about this unit? Well, once you know what 1 U stands for, then you can easily, by simply counting how many number of protons and neutrons an atom may have, you know roughly the mass of this particular atom. And if I also give you the density of a material, say the density of aluminum, okay, the bulk material density, then you know what's the total mass per cubic meter for this material, right? And since each atom has this many kilograms, then by knowing the total mass per cubic meter, I can figure out how many atoms are there per cubic meter of any material such as aluminum. So this is one of the reasons why we study the so-called atomic mass units. But we're going to revisit that in modern physics when we study atomic. Okay, now we're going to study something more interesting, the so-called scaling. Let me look at this question. You know, you probably have seen the movie Godzilla with this very, very large reptile, or King Kong, you know, an extremely large land animal. These things only exist in science fiction. Of course, we had much larger land-based animals such as a dinosaur, but these are still smaller than a Godzilla or King Kong. The question is, can something like Godzilla, this big, really exist in nature? The answer to that lies in a very simple and elegant argument called scaling. Now, in order for this animal to exist, there are many, of course, different requirements. For example, is there ample food source, right, and so forth. But let's look at just one very simple requirement. That is, for this animal to be able to move, at least you have to be able to stand up and support your own weight, right? That's a minimum requirement. Now, here is a depiction of the foot of a giant animal such as Godzilla. How much does the foot have to support? Well, you know, this has to do with the total body mass, right? The total body mass. The total body mass, how does that change when the size of the animal changes? Let's say, for simplicity, let's think of the object or the animal, whatever, using a cube. Okay, think of it as a cube. Of course, if it's not a cube, the calculation is a little bit more complicated, but the idea still is the same. Let's say the cube has a length L, okay, and of course the height is L, the width is also L. What is the volume? The volume is L to the power 3, right? It's L to the power 3. Now, what about the surface area? Say each side, the area A, is proportional not to L to the power 3, but L to the power 2, right? So you see, if the body size grows by a factor of 2, which means L becomes 2L. Okay, so linearly, an animal becomes twice as large. Linearly, okay, so L becomes 2L. How does the volume change? Well, then V becomes Instead of L, we have to use 2L, so it's 8 times the original volume, right? Because it's 2 to the power 3, that's 8. What about the surface area? Well, the surface area, 8. Instead of L squared, you must use 2L and then squared, so that becomes 4A. So you see, both the volume and the area of the animal increase, but they do not increase by the same proportion. Okay? While the volume increases 8-fold, the surface area only increases 4-fold. So imagine, here's the footprint of this animal, okay? Of this animal. If the animal doubles in linear size, so that the foot, it's from here to there, it's twice as wide and twice as deep, then everything in the animal increases by a factor of 2 in size, which means the area is now 8 times as, the volume is now 8 times as much, which means given the same density, the mass is 8 times as much, right? So it's basically 8 times as heavy as before, and yet the footprint area only increases by a factor of 4, right? So now you're using 4 times the area to support 8 times your original body weight. What does that tell you? It tells that each square inch of the contact area between the foot of the ground now hold twice as much weight as before. You see that? Okay, that means the bone has to be twice as strong in order to weight for the same cross-sectional area. Okay, so if you want to grow the linear size of the animal by a factor of 2, the bone has to be twice as strong. And if the bone is not twice as strong, then the animal will get more sluggish. It, in fact, will have difficulty even standing up, let alone jumping or whatever. So this tells you that there is a scaling reason behind why animals cannot really grow disproportionately large compared with regular size, such as the human or a monkey, whatever. You don't have something, a few miles long. Okay, because you have to use extraordinarily strong bones, probably something that does not exist in nature, in order to support the movement of this ultra-large animal. This is the idea of scaling, and that is, when you increase the size of something, quantities related to the size, such as volume, area, whatever, they may not increase proportionally by the same proportion. In other words, you have, V will increase twice as fast as A, then you have problems. Okay, so this explains why the true high jump champion of the world does not belong to any large animal, but it's a flea. The flea can jump many times its own body height, right? It can jump a few feet, yet its own size is much less than 1 inch. Can any large animal do that? Can any large animal jump hundreds of times its own body height? Not a chance. Why? Because with such a small size animal, relatively speaking, it's more agile because the bone does not have to be that strong in order to support the movement. Or if you have roughly the same strength of the bone, you can you can jump a lot higher because of the scaling reason. Another example of scaling is the so-called critical mass of atomic bomb. It is no secret that any atomic bomb requires the warhead to reach a certain critical mass. So let's see what's going on here. Okay, in a fission bomb, what you have here is what's called a chain reaction, and that is a certain nuclear fission will release neutron. Okay, will release neutron, and that neutron will further cause more nuclear decay in another nucleus, and it goes on and on and on. Okay, so the idea is that suppose you give it 1 neutron, and that causes a fission and releases more than 1 neutron. Okay, and then let's say you got 2 neutrons. That 2, each of them can create another reaction and causes 4 and causes 8 and 16, whatever. So in a few, after a few cycles, of course, you can have many neutrons, and each can cause 1 more reaction, and therefore you can double the neutron number quickly that way. So the reaction is runoff reaction. That's an explosion. But the thing is, if you take, a piece of enriched uranium, if the size of this piece is below a certain limit, if the mass is below a certain limit, no reaction like this is going to take place. Okay, it's safe. Yet when the mass reaches what's called a critical mass, it just goes off by itself. What's going on here? Well, actually, it's also a scaling reason. Let's say the radius of this uranium ball is r. Okay. Now, if r is very small, then of course you're going to have some neutrons somewhere here that are causing reaction. The number of neutrons is proportional to the volume, obviously. Okay, it's proportional to the volume. So, and that goes like r to the power 3. Right? And of course, when these neutrons are generated through nuclear reaction, some of these neutrons will go forward to cause more reactions. Some of them can actually escape through the surface. Okay, so what's the chance of a neutron escaping through the surface and become therefore useless? Well, that of course has to do with the area of the surface. The greater surface area, the more likely the neutrons can escape through it, right? The surface area goes like r to the power 2 once again. So you see, as the size grows, okay, the volume grows faster than the area because volume over area is r to the power 1. So if the radius doubles, then the volume will grow by a actual factor of 2 compared with the areas. The volume grows faster, which means you got twice many neutrons generated than the number of neutrons escaped. That is why a bigger piece of enriched uranium has more chance of these neutrons getting trapped inside, causing more nuclear reaction instead of them escaping. That is why when the mass is below a certain critical mass, nothing's going to happen. Yet over a critical mass, it's going to just spontaneously go off. Which is why in a real atomic bomb, what you have is 2 hemispheres of enriched uranium or other material separated. Each is below the critical mass. But when you combine them, it will be more than the critical mass. So what you do is you put them in a casing, okay, in a casing, and you use high explosives to push them in like this. Once they are pushed in, they become one piece. The mass is over the critical mass, and the bomb goes off. This is the idea of chain reaction and critical mass. And the reason why I'll talk about this is because, again, this is a simple example of scaling at work.